then maybe we should start. It is a great pleasure for me to open up the Colloquium series for this semester. And our first speaker is Doerte Blume. She's a professor at the Center for Quantum Research and Technology and the Homer L. Dodge Department of Physics and Astronomy at the University of Oklahoma. Of course, Doerte doesn't need any introduction because we all remember her very well from her time here at WSU. So Doerte got her PhD in 1998 from the University in Göttingen in Germany, where she worked with Peter Tönnies, who is one of the big names in liquid helium, as well as Birgitta Whaley. So she was co-supervised. After that, she went to Giller at the University of Colorado in Boulder, where she worked in the group of Professor Chris Green. And this is where she did a lot of pure body physics as well. So then she became a professor here at WSU. And in 2017, she moved to the University of Oklahoma. She's an APS fellow for contributions to physics of weakly bound quantum clusters and strongly interacting degenerate Fermi gases in one dimension. So she's an internationally recognized expert in the field of pure body physics. While she was here at WSU, she was awarded the Meyer Distinguished Professorship, the College of Arts and Sciences Mid-Career Achievement Award, and the College of Sciences Young Faculty Performance Award. And at the University of Oklahoma, she's the recipient of a Bush Lectureship. She's also very active in the scientific community. So she has served as a member of the DAMOP Executive Committee. She's remote associate editor for PRA. She's chair or has been chair of the APS Few Body Topical Group, and she's a member of the APS Committee on Scientific Publications. So we are very happy that she's here, and today she's going to talk about probing the Helium Dimer and Trimer with fast, intense lasers. Okay, welcome, Doerte.
Yeah, thank you very much, Peter, and thank you to everybody for hosting me. Of course, it would have been a lot nicer to visit in person, but maybe that has to wait a little bit. Yeah, today I'd like to tell you a little bit about the Helium Dimer and the Helium Trimer. And we're going to look at these molecules by using fast and intense lasers. And so one of the things that I'll hopefully be able to convince you of is that these sort of stickball molecules that I drew here don't really reflect the reality. So these are sort of the chemistry type pictures. And one of the things that's interesting about these helium systems is that they're actually really diffuse and broad and have a very quantum mechanical behavior. So this is work done in collaboration with Reinhard Dörner's group at Frankfurt University. That's the experimental group. The lead postdoc there is Maxim Konitzy. And this is work that's really been done over the last, say, 5 or 6 years. So it actually started when I was at WSU. And the theory person who's been leading the efforts is really Ching-Sik Wan, who got his PhD at WSU and then was a postdoc in my group here at the University of Oklahoma. So what I'll be talking about are cold helium-4 atoms and just a few of these atoms put together. And so what I'm going to do is I'm going to start by talking about the two-body physics. And here I'll be looking at real-time dynamics of the dimer. And then I move on to talking about the three-body system and specifically talk about the Efimov state of the Helium Trimer. And here, I'm not gonna discuss real-time dynamics. That's something that we're hoping to do in the future. Historically, the work was actually done in the other order. We first did the three-body work and then the two-body work. But pedagogically, I think it's much nicer to start with two and then move on to the three-body system. And these are systems that are prepared in sort of traditional molecular beam setup. But the additional thing that they have in the experiment is that in addition to having a molecular beam set up with a diffraction grating here that allows one to size separate the dimer, trimer, tetramer, and so on. In addition to that, they have intense lasers. So there's actually the possibility, one, to do pump probe spectroscopy. That's what I'm going to discuss in the context of the two-body system, but also to simply use the laser as essentially a microscope that allows one to probe the quantum mechanical density of these few-body systems. So, I mentioned a little bit that these are cold systems. So if you look at clusters that have about 10,000 atoms or so, then you can pretty nicely determine that the temperature of these systems is of the order of 0.4 Kelvin. So the physics that I'm going to discuss is where the two-body system, the three-body system, are really governed by the S-wave scattering lengths. And so we're looking at cold or ultra-cold physics. We have universal physics here. And what we want to do in this work is we want to combine this with fast and intense lasers. And both of these fields are very active right now. So cold, ultra-cold physics is an active field. Fast, intense lasers are a very hot topic. There's a lot of attosecond laser physics going on. What we want to do is we're sort of motivated by combining these two. And on the one hand, you can sort of take this perspective that if you have two good things and you combine them, should be even better. But on the other hand, you might also sort of be a little bit skeptical and say, well, if you have these rather delicate systems that are weakly bound, and these are broad quantum mechanical systems, and now you're going to come in with some intense lasers, aren't you just going to blow up the system? So what? And yes, that's what we're going to do in a sense. So in the experiments, the intense lasers coming in and sort of ripping off electrons and starting dynamics. But what I'm hoping to be able to tell you and convince you of is that this is actually fun, and we can learn something by probing the system in a way, in a rather violent manner, at least. In the case of the dimer, where we're going to look at the dynamics. So that's sort of the broader context of this. And there's quite a bit of work going on right now in the community to really combine ultra-cold or cold atom physics with fast, intense lasers. There's sort of various different directions. There's sort of a branch of physics where people are trying to use ultra-cold atoms to simulate, using these as a quantum simulator of ultra-fast processes. And there are also directions where people are really trying to say, look at atoms in a BEC, ions in a BEC, and manipulating them with intense lasers. So the work on the helium system that we've been doing falls into this sort of broader framework that's trying to sort of look at ultra-cold, in some cases, universal physics, and probing that physics or probing aspects of this through intense lasers. Okay, so let me start to maybe introduce the helium system a little bit more, because that's what we're specifically looking at. And the helium system is really a rather unique system. If you look at two helium-4 atoms, and for the most part in this talk, I'm really going to be focusing on the bosonic isotope. The helium-4 system has exactly one bound state, and this bound state has a binding energy of just the order of about 2 millikelvin. And compared to the ultra-cold, say the most weakly bound Feshbach molecules in BEC, or in ultra cold Fermi gas, this is actually pretty high energy. But on the scale of sort of chemistry, this is really an extremely weakly bound system. Just as a reference, 1 Kelvin is about 10 to the minus 4 electron volts. So this is a very, very diffuse system. In fact, the S-wave scattering length is of the order of 200 Bohr. And roughly speaking, you can simply think of this S-wave scattering length determining the size of this dimer. And this size should really be compared with the range of the interaction, which is of the order of 10 Bohr, depending on whether you want to use the effective range, that's 15 Bohr, the van der Waals length, which is 5 Bohr. You have sort of a scale separation by a factor of 10. So the scattering length is really a factor of 10 larger than the short range scale. And this is sort of indicative that the system has universal features. So it's governed by the S-wave scattering lengths, or said differently, a large portion of the probability density is outside of the interaction range of the potential. And another thing about the helium system is really that it's tractable with ab initio techniques. So what I mean by this is that the helium potential can really be calculated by quantum chemistry techniques. So it's a system where from the quantum chemistry side, we have access to the potentials, highly accurate potentials. And on the experimental side, we can look at these systems. And so there's really a nice match, or there's really an opportunity for theory and experiment to meet. And so I can already say now that all these simulations, all the theory I'm going to show you is done without an adjustable parameter. It's really all ab initio first principle calculations. So what we want to do is we want to calculate or study this dimer a little bit. We want to probe this. We want to see what the properties are. And we also want to look a little bit at the trimer. The trimer has 2 bound states. The ground state, I'm showing a density profile here. The ground state is roughly a factor of 100 more strongly bound than the dimer. So it's strongly bound compared to the dimer, but weakly bound on all other scales. And then the excited state of the trimer has a binding energy that's comparable to the dimer. So it's a very, very diffuse state. And I'm going to show you some pictures, some images later of how the trimer actually looks like. And again, just to put this a little bit more into context, if we go to the bulk system, which of course is superfluid with a transition temperature of about 2.2 Kelvin, if we look at that bulk system, the binding energy per particle is 7 Kelvin. So there's really a lot happening as we go from the trimer to the tetramer to larger systems, and the binding becomes quite a bit stronger. But again, compared to other liquids or other many-body systems, this binding energy is extremely, extremely small, and the quantum effects are really enormous in this system. So one of the interesting things about the helium, for example, is that it remains liquid under normal pressure. So how do we look at these systems? So let me talk a little bit about the experiment first to give you a feeling for how this is done. Of course, the experiment is not done by me, but by the group in Frankfurt, by Maxim Kunitsky as the lead person. So what we have is we have a nozzle on the right here. This is not shown, and you can actually adjust the pressure and the temperature in the nozzle, and you have a molecular beam coming out. So that's what's shown here. And then the molecular beam, which is relatively monoenergetic, is hitting this grating here, and this grating is essentially serving as a mass selector. So the monomer, the helium atom, is bent or diffracted differently from the dimer, from the trimer, from the tetramer. So on this side of the grating, we really have beam portions that just contain dimers, just contain trimers, just contain tetramers, and so on. And this is due to the fact that, of course, a single atom has a different mass from the dimer, has a different mass from the trimer, and that gives different diffraction angles, and then n is just the order here. So this can be isolated experimentally, and then, as I already mentioned in the Frankfurt group, they have the additional possibility to come in with femtosecond laser here, and then sort of look at portions of the beam. So you can study the dimer portion, you can study the trimer portion, and so on. So just to give you a little bit of a feeling of how this looks like, let me go back to an old paper by from Peter Tönnies' group. And again, I did my PhD with Peter Tönnies in Göttingen. So that's where I first learned about these molecular beam experiments. This is sort of one of the earlier graphs that they, earlier data that they took. Here, the temperature of the nozzle has been adjusted, and by adjusting the nozzle temperature and the pressure, what you can do is you can actually control, to some degree at least, what type of portion, what type of molecules are forming during the expansion of the beam. And so a couple of things that I want to point out here. The first thing is that if you look at the spectrum, this is as a function of the deflection angle. This is a milliradian. What you see is that for the most part, there's really, everything is dominated by the monomer portion of the beam. And these are just the different orders. So what you have to do is you have to look very carefully almost in this background, and notice this is a logarithmic scale, so you really have to be careful. And if you zoom in, what you can see is between the different monomer portions, you actually do see peaks show up, one for the dimer, one for the trimer, one for the tetramer. And by playing with the basically the experimental conditions, you can control to some degree how many dimers you get, how many trimers you get, and so on. But you're always going to be dominated by monomers. So you have to be a little bit patient and getting enough statistics from the experiment. So in this first part, where we look at the dimer, what we did is we basically sit on this dimer beam here. And then in the experiment, they come in first with a pump pulse and then with a probe pulse. The pump pulse is of the order of 300 femtosecond, and then the probe pulse is much, much shorter. So what is going to happen? So the way sort of the experiment works, the way we also looked at the theory is that first you have your dimer. So the dimer beam is such that the individual dimers are not interacting with each other. So you essentially prepare your system, your dimer, in the quantum mechanical ground state. So you have this very broad dimer wave function. And then the pump pulse comes in. It's about 300 femtoseconds and has an intensity of about 10 to the 14 watts per square centimeters. Just to give you a little bit of a reference, these parameters are such that basically the electronic degrees of freedom are not going to be activated by this pump pulse, but the degrees of freedom that are getting activated are the rotational and the vibrational degrees of freedom. So you're sort of initiating some dynamics through this pump pulse, And then the probe pulse is actually quite a bit more intense. And it's much shorter. And what this probe pulse does is the probe pulse actually rips off 2 electrons, so one from the first helium atom, one from the second one. Once the 2 helium atoms are ions, they repel each other. So you basically have Coulomb interaction between them and they fly off. And so this is called Coulomb explosion. And then the ions can actually be recorded. And by repeating the experiment over and over, you can get an image of the initial density of the system. So just to sort of, think a little bit about what is going on here, let's think a little bit about the N2 molecule. So this is a much heavier molecule. And if our molecule is spherically symmetric, as indicated here, which is, if the system is in the ground state, that's what you would have. And we take the expectation value of cosine squared theta, where the theta angle is just the angle between the electric field, the polarization direction, and the, can try to indicate this here, and the molecular axis. If that expectation value is here is 1/3, then essentially we don't have any kind of alignment. But if the molecule gets sort of deformed due to the electric field, then this expectation value is greater than 1/3. And if the molecule is sort of squished, this expectation value is less than 1/3. And what is being done in these experiments and also theory of much heavier molecules, so for example N2, is that if you shine the laser onto the system and you're in the so-called impulse regime, then what happens is that you really see this nice regular pattern here. So you see alignment of the molecule, and then you see revivals, because what you have, it's basically you have this rigid rotor molecule where the energy level spacings are regular, right? We know that these are the energy levels of the rigid rotor molecule, and then because the energy levels are multiple integers of each other, you actually see this alignment signal. However, in the adiabatic regime, what happens is basically the molecule sort of follows the pulse, so it gets aligned with the pulse, and then it sort of goes back to being spherically symmetric. So this is the adiabatic regime. And aligning the molecules aligning molecules, that's really what we want to do with the Helium Dimer system as well. So when we discussed with the experimental group, and they were sort of discussing what they can do, one of the goals, one of the motivations they had in mind is really looking at the alignment of the Helium Dimer. Of course, there are a number of differences between N2 and the Helium Dimer. And one of the differences is, as I mentioned earlier, the Helium Dimer does only have a single bound state, versus N2 is really more or less a rigid rotor and has many rotationally bound states. So it's an interesting question to ask, what is really happening in the case of the Helium Dimer? And sort of the way we think about this question is that what we would really like to do is we would like to sort of add the term physical dynamics to the list of things that people are looking at. So if I go back to the previous slide here, talking about the alignment of N2, then I think about this as sort of chemical dynamics. So we have sort of rigid rotor type physics. And in our case, the initial state is very, very broad. So we don't really expect this rigid rotor type model to work in our case. So said differently, what we sort of expect is that if we look at the helium dimer, it's an entirely new regime because we only have one bound state. It's extremely weakly bound. And moreover, we have a rather large separation of scales. So the binding energy, as I mentioned, is about 1 millikelvin, which corresponds to 50 nanoseconds. But the pulse, the pump pulse that we're applying is of the order of 300 femtoseconds. And so when we started thinking about this, we looked a little bit at the literature, and there are different predictions for what would happen for the helium dimer, but none of the theory predictions actually agree. So there was sort of a big need not only to do the theory, but also to look at it experimentally. And this is what is found, what was measured experimentally. So let me walk you through this. So this is what we call kicking the helium dimer. And what we're looking at is really the expectation value of cosine squared theta. Again, if that value is 1/3, it means that the system is spherically symmetric. And it means that essentially we did not succeed in actually aligning the molecule. Now, if you look at this, the first thing you notice is that indeed we do see some sort of alignment because we do have deviations from this value of 1/3. And if you look at this sort of for the first time, you might be reminded of an interference pattern. And I will show and hopefully convince you that indeed there is an interference going on in this system. So what exactly are we looking at here? So the sequence is just as I said before, we have a pump pulse, then we wait for a delay time, and the delay time is what's shown here. And then we probe the system using Coulomb explosions. So this just means we essentially instantaneously rip off the electrons, and that allows us to basically image the quantum mechanical density. And the what's plotted on the y-axis here, that's the helium-helium distance. So we're really looking at the alignment signal, this cosine squared theta, as a function of the helium-helium distance for different delay times. And this is the image that you get. So one of things I want to do in the following is discuss a little bit how to understand this, these results. And so to look at this theoretically, we basically do the same thing. We simulate the pump pulse. We use a fairly simple Hamiltonian for this. So we just take a Gaussian profile with the widths or the intensity and the time lengths of this pulse being determined from experiment. And then we stick in the polarizabilities that have been calculated experimentally. That have been calculated theoretically using quantum chemistry techniques. And so what happens is when the pump pulse is applied, the pump essentially moves a little bit of population from the J is 0, from the rotationless initial state to the J is 2 and J is 4 rotational states. So essentially, it's just promoting some fraction of the initial state to excited states, and the J is 2 and J is 4 channels do not actually support bound states. And one thing that you see here is that the laser essentially grabs on in the very, very small distance region. So this is our initial density. So this is the dimer state on a log scale here. And the laser really just grabs on to the innermost portion of this wave packet in a very localized region. And so if we use this, again, it's a parameter-free theory. If we use this and then compare with the experimental image, this is what we see. We really see very beautiful agreement between the simulations and the experiment here. So one additional thing that we do put into the simulations is actually the resolution that they have in the experiment. And I mean, this is a small detail, but it is interesting that by looking at the experimental data, first, we did not include the finite spatial resolution that they have in their imaging, and we did not get nice agreement. But if we then include the experimentally measured spatial resolution, we really get very, very nice agreement between the experimental result and the experiment and the theoretical result. And if we analyze our simulations, and we can actually make an essentially analytical model of how the pulse grabs on, how the pump pulse grabs onto the initial wave packet. If we do this, what we see is that essentially we have a very small JS2 partial wave portion that is moving outward basically on a very broad structureless background, namely the initial J0 state. And so essentially we have an interference between two different partial waves. And what you're seeing here is really the interference of a JS2 partial wave with a J0 partial wave. So it's essentially an interferometric measurement, or it's a measurement that can be interpreted analogous to the double slit experiment or double slit setup. So just to sort of summarize this part, so these experiments with the supporting theory really for the first time looked at the dynamics of the very weakly bound helium dimer. And the significance of this is that this is really an initial state that's dominated by universal physics, just by the S-wave scattering lengths. And the other new and interesting aspect of this is that we were really able to then look at the system with single atom resolution. We did see that the helium dimer can be aligned, even though it's in quotation marks rotationless helium dimer, because there's only one bound state. But it's really the continuum portion of the wave packet that got aligned. So I should sort of stress this. And the alignment signal can really be interpreted in terms of an interference between the JS0 and JS2 partial wave channels. And so essentially what this means is that we were able to measure, or this experiment is able to really measure the relative phase between the two different partial wave components as a function of time, as a function of the delay time, and also as a function of the internuclear distance between the two helium atoms. So this is just stressing again that this is not a rigid rotor state at all. So there are many outstanding questions here. And one of the things that ideally we would like to do is we would like to use this technique to really look at resonances, much in the same way as we're looking at Feshbach resonances in ultra-cold systems. And to do this, one really needs longer pulses than are currently available. That's a challenge experimentally, although we're somewhat confident that the next generation of experiment can sort of look at this. And we also want to look at the dynamics of the Trimer system, but to do this, we really need to first populate, and we are particularly interested in this excited Helium Trimer state, which is an Efimov state. And so we need to populate this first. So let me tell you a little bit about the prospects of the tunability of the Helium Dimer system first. So this is where we did some calculations, and we really cranked up the laser intensity quite a bit here, and we assume that the pulse is essentially infinitely long. And so what you can really see is that looking at the helium-4 system, and now also the helium-3 system, and 2 helium-3 atoms, what you can see is that if one had these lasers, long pulses, intense pulses, one could actually tune the system and induce new bound states into the system. So this point here would correspond to the second bound state of the helium dimer being pulled in. And so this would be where we have resonance. And this is sort of where we would like to be. In the helium-3, helium-4 system, these resonances occur at lower field strengths. So this is nice. And of course, it's hard these days, at least, to work with helium-3 because it's just hard to get and very expensive. But the nice thing is that in principle, this tunability works. And if we do some time-dependent simulations, so if we do pump pulse spectroscopy simulations, and we just pretend that we can increase the pulse lengths from 0.5 picosecond to 8 picoseconds and look at relatively strong laser pulses, then you can actually see signatures here of revivals. And this is now somewhat similar to what we had previously seen in the rigid rotor type molecules. But to get here experimentally, this is rather challenging. But I think as an outlook, this is quite nice, and this is good to keep in mind. So in the remaining few minutes, I just want to talk a tiny bit about the Helium Trimer. And as I mentioned earlier, we did not do any time dynamics on the system, but we've looked at the static properties, or said differently, the structural properties of the Helium Trimer excited state. So the next step here would be to do the dynamics, but this is a rather challenging topic, both experimentally and theoretically. So let me tell you a little bit about this Helium Trimer excited state. As I said, historically, this is work that we did before we did the Helium Dimer work. And so the trimer is interesting because it's an Efimov state. An Efimov state is a rather unique three-body state where the system has a discrete scale invariance. There's sort of two aspects to this. So one is that if the scattering length is infinitely large, which it isn't in the helium system, it's just large. But if it was infinitely large, we would have an infinite number of three-body bound states, at least in theory. Of course, having an infinite number of bound states is nothing unique. Even the hydrogen atom, written here in atomic units, has an infinite number of bound states. But the other thing is that in the three-body system, again, if you go to the infinite scattering length regime, what you need is you sort of to get the type of physics that I'll be talking about, as opposed to a 1/r potential, you need a 1/r² potential. And you might say, well, how do you get a 1/r² potential? It turns out you can get this in the three-body system if you think about this little r here as your hyperradius, which is sort of just the size of the three-body system. So the key point here is that in this three-body system, and this was realized by Efimov in the 70s, in this three-body system, you do need what's called a three-body parameter. You need to specify the short-range boundary condition. Unless you do this, you don't actually know where your energy levels lie. And this is sort of the theory perspective. From sort of a more practical point of view, you can turn this around and you can say, of course, if you have a real system, your energy levels sit somewhere. And that means that there has to be some scale, some short distance scale in your problem that fixes where your energy levels lie. And this sort of leads to a discrete scale invariance of the Hamiltonian. So this three-body system, even though there are a lot of details to discuss, for now, just believe me that it's rather unique. This is sort of the tower of three-body states that I mentioned when the scattering length is very large. Another aspect is that if we know this three-body parameter that I mentioned, then the whole energy spectrum as a function of the scattering length is known. So this is part of the system's universality. And then we might say, okay, we talked about the helium system. So where does helium lie here? So these are two curves from this Efimov plot that I showed before. This is the Trimer energy on a funny scale. This is essentially 1 over the scattering length on a funny scale. And these are two of the many curves that I'd shown you before. So I'm just taking the lowest curve and the next curve here. And then on this graph, the Helium Trimer sits exactly here. So as I said, the Helium Trimer has a specific scattering length, and that turns out to be where this green bar is. And so what we see from this is that the excited state follows the solid line very nicely. So this is actually predicted to be an Efimov state. And what we then looked at, sort of using the very same technique as before, except we're not using the pump pulse, we just probe the system, so we don't initiate any dynamics. First thing we can see is we can actually look at the, convince ourselves that the Helium Trimer excited state exists. So this is done by measuring the kinetic energy release. So essentially, this is the sum of the 3 Coulomb interactions here. And of course, the helium system itself is not Coulomb interacting, it's van der Waals interaction. But remember, to probe the system, we rip off one electron, and so that converts the interactions to Coulomb interactions. And so by measuring this kinetic energy release, you actually can see the existence of the excited trimer here. If you have large internuclear distances, the kinetic energy release is small. So this is the signature of the excited trimer. And over here, there's a big blob that I'm actually cutting off. And that's the ground state, which is much more tightly bound. So let me just give you maybe one more plot before I finish up to sort of stay in time. So from these measurements, I mentioned that you can extract the probability distribution of the trimer. Then you can analyze the different configurations. And this is what we found, what was found from the experiment, looking at just the excited state portion of the helium trimer beam. Visually, this looks very similar to the theoretical calculations, and it looks very different from the ground state of the system. So just to orient you here, so what I'm plotting is, what we're doing here is the following. We have 3 helium-4 atoms. We pick 2 of them. And the way we pick them is we pick the longest distance in the trimer. And the 2 atoms are fixed, and we assign a unit length of 1 to them. And we put them at -0.5 and +0.5. So we're looking at normalized configurations of the system. And then this color plot here shows the probability to find the 3rd atom. So for the ground state in these calculations, it's also been measured, but these are the calculations. What you see is that essentially all the different configurations are present. So you have a triangle where, the 3rd atom is the same distance, or we have this triangle, you have particles sitting on a line. If you go to the excited state, it's much more likely to find 2 particles relatively close to each other, with the 3rd one far away. There's a sort of a 2 + 1 or dimer plus atom configuration. And so there's really 2 things that I want to stress here. One is this is a reconstruction of the quantum mechanical trimer density. So this is really nice. It's just beautiful to look at quantum mechanical densities with this resolution. And the other thing is that the ground state of the helium trimer and the excited state of the helium trimer look rather distinct. And that is supporting the understanding that the helium trimer excited state is a relatively pure Efimov state, but the helium trimer ground state really shows some deviations from the ideal Efimov scenario. So there are finite range corrections that play a significant role. So what did I talk about? I talked about an experimental technique, namely Coulomb explosion imaging. And that really allowed to look at these few body systems. And we applied this to 2 different cases, the Helium Dimer and the Helium Trimer. In the case of the Helium Dimer, we first applied a pump pulse and studied the theoretical description of it. It's sort of like kicking a dimer and then looking at how the weakly bound non-rigid rotor molecule responds. And in the case of the helium trimer, we did not actually use a pump pulse. We really just, in quotation mark, prepared the initial state and then looked at the density of the state prepared. And so what we want to look at in the future is really looking at the four-body system, looking at excited states, and really looking at dynamics of universal systems with single atom resolution, and then connect this, for example, with studies that are currently going on in the ultra cold regime. So with this, just sort of show my second slide again, the outline, and thank Qingze, who did the theory calculations, and also thank Maxime and Reinhard for the collaboration. And thank you for your attention.
Yeah, thank you very much, and big round of applause. Yeah, thank you very much for this beautiful and colorful and also very pedagogic talk. I think we learned a lot. Are there any questions from the audience? Don't know how I could see all of you, but if someone has a question, please just chime in here.
I have a question, if that's all right. First off, first I want to say I really enjoyed the talk. Thank you. Secondly, with the excited state of the Helium Trimer, you mentioned that we had two atoms that are really close together, and then one atom that was far away. Regarding the distance between the close atoms, how does that compare with the ground state of the Helium Dimer?
Yeah, that's a very good question. So roughly you can think about the, I mean, this is just a sketch here, right? This is one of the possible configurations, but roughly speaking, you can really think about this as you essentially have a dimer. So it's roughly of the distance that you would have in the dimer. And then you have sort of a third atom dangling far apart. So this is really a huge, huge system. And so, you can really sort of think about it as, the third one, the third guy here is almost unbound. It's just sort of hanging on to it. And, this one has a binding energy of about 2 millikelvin or so. So it's really very weakly bound.
Mm-hmm. And so the Efimov trimer lives on the repulsive side, right? So where you already have the dimer curve, and then you go down from there.
Yeah.
Okay.
And Ethan, if you wanna, coming back to the first question, if you look at the pair distribution function here, this is the probability to find two atoms at a certain distance. This is on a log scale, so you have to keep this in mind. And so you really go out to about 300 angstroms or so. And this is for the trimer excited state. This is the trimer ground state here, which is really quite a bit smaller.
Thank you.
And then just to Peter, I think this is the plot, right? So this is really the scattering lengths for the helium system is positive. So we are really sitting on the repulsive portion here.
Yeah, and then what was this beta, larger or smaller than 1 in that plot?
Oh, this is sort of a scaling factor. Of course, the helium system. So this is, I sort of, in a way, I cheated a little bit in that I said, the helium system is so great because we can treat it by ab initio techniques. And, of course, that is true. The disadvantage that I didn't highlight so much is that at this point, we don't have the same tunability in this system as you would have by Feshbach resonances in the ultra cold. So there you can actually change the scattering lengths through the application of magnetic field. In our case, in this plot, what I simply did And this is what's done in quite a few theory calculations. I simply scaled the helium-helium potential. So I make it a little bit less attractive when beta is less than 1, or I make it a little bit more attractive when beta is larger than 1.
Okay.
And that is really the scaling factor here. So it's mimicking the effect of changing the S-wave scattering lengths, but it's really not done in a physical way. This is a theory plot.
Okay, yeah, thank you.
And when you say that everything's ab initioly determined, are the potentials themselves calculated from first principle to appropriate accuracy, or do you have to put some measured parameters in there?
No, it's fully ab initio. I mean, these are not things that we've calculated, but the Born-Oppenheimer potential curves, so basically solving the electronic Schrödinger equation and sort of integrating out the electronic motion, that is done with ab initio techniques, because you have basically 4 electrons. So that's
and Born-Oppenheimer is good enough to get all the agreement. And
yeah, I mean, they do include relativistic corrections to some degree in these potential curves, and everything up to, you know, C7 is included. So you have retardation effects in there. C6, C8, C10, C12, I think it's going up to C16 in terms of parameters. They're all calculated. And you don't actually need to do any tweaking in the inner region. So it's all calculated by ab initio techniques.
then if you want to do this with just an effective theory and putting, how many terms do you have to go in before you know to get a good enough agreement?
So this is actually an interesting question. So the effective range effects in the helium dimer in terms of the binding energy, that's about 10%. So if you're interested in true low energy properties, I would say including scattering lengths and effective range is correct. It's all you need. Now, in this case, I mentioned this a little bit at the beginning, that when the laser grabs onto the molecular wave packet, it does this in the very, very inner region of the molecule, or of the, you know, sort of when the wave functions almost decayed to 0. And so what this is saying is that this experiment is actually in some sense sensitive to the most non-universal part of the dimer. And in that sense, it's not so clear to me how many parameters we would need to really reproduce this type of situation. So what we do know is that to simulate the pulse, the pump pulse, we can basically use a delta function. If I'd shown you results with a delta function, it comes in and hits the dimer, and then you sort of ask what happens. So I mean, it's like literally you sort of come in with a hammer, boom, and then, you know, it's very short, and you just wait for what happens. So I actually don't know the answer to how many parameters you would need to sort of describe that inner portion, or how universal that is. So that's an interesting question.
But you're working with the actual potential form.
Yeah, we
so
do.
Sort of, I'm just thinking about the analog in nuclear physics, where people worked for a long time with potentials, and now everyone's going to chiral effective theory. But then, you know, there's the question of how far you have to go. And
yeah, it's, you know, I mean, there's actually an interesting connection to the nuclear physics, because there, the 10 contact, or the contact, is sort of in a way measuring how steep that initial turn on is, right? The contact in nuclear physics, at least this is my interpretation, is not exactly the same as the contact in atomic physics. Now, there are people who disagree with my understanding, just, but that's my understanding. And so it could be that this concept of the nuclear contact at least the way I understand it, then that could actually be helpful here, because there's sort of a van der Waals universality that's coming in here that might be using it. Sort of, it's not really van der Waals universality, it's just the steepness of the potential when that wave function gets turned on.
I have one other question. Oh, Phil.
Yeah, well, it's not related to what you presented, but it's something that you would know about. Okay, and that has to do with if you build up the cluster by adding helium-4. My question has to do with the transition to droplets. So how well is it understood if you have cold helium-4 and build up the cluster? At what point do you start seeing quantum circulation effects if you spin a cluster?
Yeah, so you need about 60 atoms to get microscopic superfluidity. And so in terms of, I think what you're asking about, that's when you sort of start seeing a signature of the Roton minimum. And that's
where do I find that discussed?
I can send you a paper. If you search for Andrei Vilesov and Peter Ingenious, you will find it.
Okay, so that's part number one. Then part number two is how many atoms do you need before you start seeing the shape modes of the droplet? Okay, so many decades ago we studied, shape oscillations of drops and bubbles and so on, and they would be very high Q for ultra cold helium droplets. So I'm curious to what how big a cluster do you need before you start seeing those modes? I believe Humphrey Maris studied that at one time for large things, but I don't know how small people have gone.
So these would be sort of surface modes,
yeah,
for example.
Surface mode, the droplets. Anyway, I'm just curious because it's something you probably would have thought about one time or another. So I thought that, well, it's in the sort of the continuum direction, which is more my background.
Yeah, so for that, I don't actually know the answer. I do know that it does show up, when you have 10,000 or 1,000 atoms, but I'm not actually aware, but that's probably just my ignorance of experiments or theory that's really looking at the transition. You're sort of asking the transition to collective modes.
Yes. So Humphrey Maris at Brown, toward the end of his career, so sometime around 2000, did some studies, but I don't remember how small he went. Thank you.
I have got another question, and I didn't quite catch, Doerte, when you said you made the pulse length longer, or you want to make the pulse longer, and that will draw in additional bound states into the dimer system. Is there a good way of understanding what the pulse is doing to produce additional bound states, or what's the mechanism behind that?
Yeah, it's so essentially what you have is you have the polarizability of the molecule. So that's the physical mechanism. So if you think about, just say a diatomic molecule in an electric field in the ultra cold, there would be exactly the same effect. So if you look at the interaction, it's essentially the same Hamiltonian here. So the way you can think about is that if you have your polarization direction up, so what's happening is that you actually sort of have, your molecule, as opposed to being round, if you want strictly symmetric, gets elongated. And so, you know, think about dipole-dipole interaction. So if your system sits like this versus this, you get attraction, repulsion. And so depending on the angle in one direction, you really get a deep pocket, and in the other direction, you get a repulsion. And that deep pocket is sort of deep enough to then support these bound states. And they actually have a fairly big angular dependence.
Okay, I see. Okay. Michael, you still had another question?
Oh, just a simple question. In the initial beam of dimers, trimers, etc., is the relative population predictable basically from a thermal ensemble of the initial states and some chemistry, or?
That's actually a good question. So the formation of these small clusters is not overly well understood. So, you know, you have basically atoms coming out of the source, and then the atoms travel downstream, if you want, in the beam. And then there are collisions between the particles, and that leads to the formation of dimers and trimers and so on. So you can sort of imagine several ways that these clusters are forming. You know, if you think about you want to get a trimer, you could imagine you have 3 atoms come together and then form a trimer. Or you could think about first you form a dimer, and then you have a dimer colliding, and then with an atom. I mean, of course, you always need another particle to take energy away, but you know, essentially you have 2 + 1 that are then forming a trimer, and that's actually what's happening. So when Tönnies originally, I mean, you know, he really dedicated a lot of time of his career to studying these systems. And his dream was really to see the helium trimer, and they could not find the helium excited trimer state. And the reason was that what they did is they sort of optimized their nozzle conditions, their source conditions. So it's basically the pressure and the temperature of the source, such that they would get more and more ground state trimers. And they were hoping if they get more ground state trimers, they're also going to get more excited state trimers. And then in a way, sort of the thing that Maxime did is he didn't optimize the trimer yield, he optimized the dimer yield. And by doing that, you actually produce more of the excited trimers. So there's, there's some understanding of that mechanism, but there's no full model that really predicts this. So I would say it's incomplete at this point.
And you're starting from a liquid essentially, so it's not a thermal thing. It's really this dynamics down the.
Yeah, you have an isentropic expansion.
Yeah, interesting.
Do you remember correctly that Doerte also looked at other atoms like a neon trimer and found it to be like an equilateral triangle and these things?
Yeah. So they've looked at a lot of things. So something I didn't sort of stress, this so-called Coulomb microscope, this Coulomb explosion technique. I mean, they've used this for other noble gases, so for comparison. And that's actually how some of the calibration for the ionization is done. So there's a lot of calibration that goes into this work. But then they've also looked at, DNA basically, and really big, chemically relevant molecules. So they have sort of a whole range of molecules that they look at. A big focus is also to study chirality and to really understand, how does that asymmetry that you have in these molecules, how can you use this possibly by changing, say, the polarization, changing intensity when you probe the system.
Cool, yeah. All right, do we have any further questions?
I have one more if it's okay.
Sure. Go ahead.
Doerte, you were talking about with one of our squared potential, we get this nice scaling of energy levels, but in order to pin down where the energy levels actually lie, you have to put in a short range boundary condition. I was wondering if you could tell me what that looks like in practice. Like, what does that mean to put in a short range boundary condition?
Yeah, so for our calculations here, that boundary condition is actually in there already because the helium-helium potential is not a sort of pure delta function interaction, obviously. So it already has a scale. And so in that sense, you can say that the van der Waals scale is already setting that boundary condition. If I had used, like Efimov, just pure two-body delta function interactions, what I would do is, for example, in the hyperradius, which is sort of this collective three-body coordinate, in the hyperradius, I would just put, say, a hard wall at some distance, and that would fix where the energy levels are. So I think that's actually very similar to what you did, Ethan, in your 1D studies when you said you have a 1/x² potential and you need to regularize this somewhere. So you just say your wave function has to go to 0 at some point, at some sufficiently small x, but x greater than 0.
I think that was Sean's project, but he told me about it, so I know what you're talking about.
Sorry, Sean.
Thank you.
All right. Any further questions? Well, if not, then let's give Doerte another big round of applause. Thank you very much, Doerte.
Yeah, thank you for having me. I appreciate it.
Always a pleasure.